All right, guys, this is going to seem like we're kind of taking a detour from what we were doing yesterday with graphing parabolas, but there is going to be a connection to what we're doing here and what we're going to be seeing in upcoming sections. So today we're going to just do some quick review of some basic factoring techniques. In the previous unit, when we were using prime factorization of numbers to simplify different radicals, we were basically breaking down a number into its smallest possible pieces. The example up at the top here says we can take the number 72 and break it down into 2 times 2 times 2 times 3 times 3, and that is the prime factorization of 72. So we can take a number, a bigger number, a composite number, and break it down into its smallest possible pieces. We can use a similar process to factor actual algebraic expressions that have variables in them as well. So for each one of these techniques that we're going to just kind of review, I'm going to start with the way that we would have seen it more recently with the simplifying, multiplying, distributing, foiling, and then we'll review how to factor those. So in our first example here, I'm asking you to just distribute 3x into 2x minus 5. And when we do that, we're going to multiply 3x times 2x, and that gives us 6x squared. And then minus, we multiply 3x times 5, and we get 15x. The factoring now is reversing that process. So essentially, I want you to undistribute that. We're going to go from right to left of that equal sign rather than left to right. So the first thing that we need to do is we need to determine or find what we call the greatest common factor. Greatest just means biggest. Common means what they share. Factor means the component of the two pieces or numbers. You might remember this as being called the GCF. So once we find the GCF, we're going to pull that GCF out front, and then we're going to leave whatever's left over behind after we essentially undistribute that or divide it from each of the terms. So if we look at this first example, I notice that we've got 5n and 20. The GCF between those two numbers is 5. So I'm going to factor a 5 out to the front and then determine what would be left inside if I undistributed a 5. And when I say undistributed, I'm basically saying divide. So 5n divided by 5 is just the n, and 20 divided by 5 is just the 4. Notice if I were to redistribute that 5, we would get back that original problem, 5n plus 20. In our next example, we don't have a coefficient in front of the x squared, so remember that's just assumed to be 1. So the GCF between 1 and anything is just that other number, so it's 8. Between 1 and anything is just 1 itself, so really essentially saying there's no proper common factor. But notice that both of these terms have an x in common. So we're going to say that the GCF for these two terms is just x. So I'm going to factor out or undistribute an x from those two terms, and it leaves me behind an x minus 8. Notice, again, if I redistribute the x into those two terms, I'd be left with the original expression. In our last example, I've got 4a squared and 14a. The GCF between those two is 2a. They both have a 2 in common. They both have an a in common. So I'm going to factor a 2a out. And then when we undistribute that 2a, or rather divide both of those terms by 2a, we're left with 2a and then plus 7. Again, if I redistributed that 2a, we would be left with that original expression. Pause the video now and try problems 1 and 2 on my math lab to practice factoring out a GCF. All right, our next type of factoring that we wanted to take a look at is what happens when we try to undo some foiling. Now notice that this is a special type of FOIL. We've got x minus 7 and x plus 7. Let's see what happens when we FOIL these together. So my firsts are going to give me x squared. My outer terms give me positive 7x. My inner terms give me negative 7x. And then my last terms give me negative 49. When we try to combine those outer and inner terms, they just cancel each other out, which means that I would be left with just x squared minus 49. This is a special situation because we did get those two things to cancel out. What basically we were left with is called the difference meaning subtraction, of perfect squares. What we're left with are two perfect squares, x squared and 49, and the subtraction of them. So the basic pattern that we're trying to use here is that when I've got the difference of two perfect squares, then we're going to basically unfoil that as a plus b and then a minus b. Like this would have started as x squared minus 49 and factored down to x minus 7 and x plus 7. It doesn't matter which one's positive or which one's negative because the two pieces inside are the same. So notice that here with x squared minus 144, they're perfect squares. So we're going to unfoil that and factor it down into x plus 12 and x minus 12. Likewise, with our next example, we've got a number 9 in front of that x squared, but it's still perfect, so we can factor that down into unfoiling it as 3x plus 5 and 3x minus 5. Okay. Pause this now and try the next couple of problems on the MyMathLab. Okay, what happens when we don't get that special foiling relationship to happen when we don't have minus 7 and plus 7, but in this case we've got minus 3 and plus 7? Well, if I FOIL it out, I get x squared, still plus 7x, but now it's minus 3x, and then the last give me minus 21. These middle two terms don't cancel, but they still can combine, and when I combine them, I get x squared plus 4x minus 21. Notice that those two numbers that we started with when we go to unfoil that, the two numbers that we start with, negative 3 and positive 7, if we multiply those two numbers together, we get negative 21, which is the L of FOIL. And if we add them together, we get positive 4, which is basically the combination of the O and the I of FOIL. So we're going to use that pattern of numbers to unfoil the next two expressions by noticing that with this first one, we're trying to find two numbers that when I multiply them together, I get 12, the L of FOIL. And when I add them together, I get 7, the combined O and I of FOIL. And if you haven't guessed it already, when I try to figure that out, that's going to be the numbers 3 and 4. 3 times 4 is 12. 3 plus 4 is 7. So I'm going to unfoil this, give myself two sets of parentheses, put an X and an X in the first spots, and then put my plus 3 and plus 4 in those second two spots. So that is the unfoiling of that expression. In the next one, notice that I'm looking for two numbers that when I multiply them, I get the L, which is negative 24. And when I add them, I get the combined OI, which is negative 10. So I'm looking for two numbers that when I multiply them, I get negative 24. But when I add them, I get negative 10. If you think about the factors of 24, two things that multiply to equal 24, we got 1 and 24. That's not going to work. We got 2 and 12. 3 and 8, 4 and 6, but we need two numbers that are going to multiply to equal negative 24, so we need them to have different signs, and that's actually going to be negative 12 and positive 2. If you were thinking about using 4 and 6, in order for us to have two numbers that multiply to equal negative, one of them would have to be negative and one of them would have to be positive, and that wouldn't work here, so it's got to be negative 12 and positive 2. So when I set it up into those parentheses, I've got my x and my x, and then a minus 12 and a positive 2. And we've now unfoiled that. Pause the video, try the next two problems on MyMathLab. Okay, what do we notice when we factor these? So there's still those unfoil type problems. Notice that in this case, I'm looking to multiply two numbers to get 9 and add those two same numbers and get 6. And you should be able to tell that that's going to be, when I choose 3 and 3, the same number. So to unfoil this, we're going to get x plus 3 and then another x plus 3. And a simpler way of writing that would just be x plus 3 and then the quantity of that squared. Those are the same. It doesn't matter which way you write it, but I just wanted you to be able to recognize that. And then notice if you look at this next one, we want to multiply two numbers to equal 36 and then add those same two numbers and get negative 12. And the only two numbers that actually do that are negative 6 and negative 6. Again, they're coming out to be the exact same. So when I put those in my parentheses, we're going to get x minus 6 and x minus 6, or we could write it as x minus 6 squared. So these two original problems are special. They're what we call perfect square trinomials. Remember, trinomial just means it's got three terms. And this is a perfect square trinomial because these were the result of squaring a binomial. If we were to square x minus 6 or square x plus 3, we would have gotten those original expressions that were given. We're just asked to go in the other direction. So the basic idea here is that if I square something like a plus b, then we get this pattern where we square A, and then we double the product, meaning I double A times B, because we get two of them, one from the O, one from the I, and then we square the second to get the last terms. Okay? If there happened to be a minus between them, like in the second example, then that first sign turns into a minus, but the last one is still a plus, because a negative times a negative is positive. And what we want to just be able to recognize is going in the reverse. That if I started with something where we can recognize that the middle term is double -6, and then the last term is -6 squared, then we can recognize that and maybe shortcut that a little bit. Okay? So on these last two examples, notice that I want you to fill in the blank with the constant, and that just means the number, that will make a perfect square trinomial. I want to force this pattern of a squared plus 2ab and then plus b squared. Notice that the term that we're given is 10. So 10 is 2 times something times x. So if I take 10 and I divide it by 2, I get 5. And then we're going to use that 5 and square it to put that final number there on the end. That would be 25. Now I've made this a perfect square trinomial. So if I go to factor this, I know it's going to be perfectly x plus 5 times x plus 5, or x plus 5 squared. On this next one, same thing. I'm going to take that -22, and I'm going to divide it by 2, which gives me -11. Now, if we think about when I square -11, that's going to be a positive number, and that's going to be positive 121. So if I wanted to factor that down, it's going to be x minus 11 times x minus 11 perfectly, or I can just write it as x minus 11 squared. All right, now that you've got a chance to practice these, go ahead and try those last few problems with the perfect square trinomials on the My Math Lab, and you'll be all ready for what we're going to be doing on Monday. Good luck.